Welcome to a lesson with Dr. Powell. Let's take a minute and look at um, polynomials with real coefficients, and we'll look at a merge of those. Now, this is the notation for polynomials with real coefficients. Things like 2 plus x, or even square root of 3 plus 2x plus x to the fifth. Real coefficients. So this is, and these are examples of things that live in here. So let's suppose that's our domain. And let's make a function with this is our domain. And let's suppose that we require that let's require that x plus 2 actually goes to 0. That x plus 2 and 0 are in the same fiber. And let's also suppose that addition between polynomials is preserved. The question then is, what are all the fibers look like in this case, if we require that addition to be preserved in that particular sense? Okay, so let's take a look at that for a minute. All right, so let's suppose that we want addition to be preserved, but let's also add another thing, and let's suppose that we want multiplication to be preserved, meaning that if we have like f of a times b, we want that to go on the outside as well. Okay, so let's require addition and multiplication to be preserved in this particular case. So then how big should the fibers be, right? Well, if we take x plus 2, let's just kind of think for this for a minute. If we had x plus 2 times anything, let's just do that times some other polynomial. And we want to preserve the operation. So that means that f of that and f of that would be equal to f of x plus 2 times p of x. Well, notice that since we require that that x plus 2 goes to the same place as 0, and 0, things that preserve, let's see, what does that do? Okay, so this has the same image. Well, we could put that back as f of 0 times p of x. That actually means that well, this is 0. So, so that means that but we know that x plus 2 is in the same fiber as 0. So, okay, so f of x is in the same, so x plus 2 is in the same, already we know is in the same fiber as 0 here, and we know that this is equal to f of 0. Oh, so we know these two are the same, so they have the same image, so therefore this guy is in the same fiber as 0. So really kind of what we've done is the fiber that contains 0, I'll call it 0 bar, contains x plus 2. Not only does it contain x plus 2, it actually contains all multiples of x plus 2. Well, that's kind of interesting because anytime we have anything at all, like any other polynomial at all, like q of x, and we add 0 to it, 0 is actually replaceable, at least in the image. You could get to f of 0 by preservation of addition. So if we go f of 0 and f of qx, you could actually get to f of 0 by replacing 0 before with anything in its same fiber. Actually, multiples of x plus 2, right? Multiples of x plus 2 can replace 0 before. So basically what we know is that q of x plus x plus 2 times anything at all are in the same fiber as q of x. So just adding by a multiple of x plus 2 in this within these polynomials gives us a whole fiber or at least part of a fiber, a whole chunk that has to go together. In fact, we could even just say, well, we have only, and actually that came from an addition idea too, because we're requiring addition to be preserved. So, I mean, we could say, oh, is this a choice good enough? So we've made a choice. Maybe that's what we should do. Our choice of fibers are things that are, so we're going to put our chunks so that they're a multiple of x plus 2 apart, instead of being like a multiple of 2 apart or 5 apart or whatever when we're doing skip pattern merges in Z. Why don't we look right here and say it's a multiple of x plus 2 apart within polynomials? Are those, so that's our choice. And we can actually, if there's a notation for this, we can write this down, x plus 2. Okay, so that's our choice of skip pattern merge x plus 2 apart. Is this choice good enough for um, the preservation of addition and multiplication if I just did it that way? So, I mean, we could just try different things out here and see if that would actually hold. So for instance, let's suppose that we had, so bar will be representing taking a fiber in this particular partitioning. So let's, based upon our technical example before, really all we need to do is if we replace a of x by anything within its own fiber and b of x by anything within its fiber, then do we still get this before we replace? Okay, and that actually will give it to us based upon the same idea before. So basically, can we replace this with anything in the fiber, anything in the fiber, and this addition still and still kind of always arrive at the exact same thing right here with this from before. So let's take a look at that. So we have a of x plus, now how can it vary? It can vary by a multiple, let me use q, a multiple of x plus 2. And this guy right here can vary by a multiple of x plus 2 as well. The argument looks pretty much the same because we can factor an x plus 2 from there and get another multiple, so it really does work. Addition really is preserved in this particular case. Let's see, is multiplication preserved? So we can look at that as well. So a of x plus some multiple of x plus 2, so something times x plus 2. Okay, and b of x plus something times x plus 2. And how does that work? So with the foiling process, you'll notice that, let's see, we end up getting, so we get this, but all the other terms are actually going to have an x plus 2 in them. So it'll be a multiple of x plus 2. And then we're going to have a of x times b of x plus some multiple of x plus 2. So it actually, which actually is contained in a of x times b of x, which means that even if you vary the representative of a of x and the representative of b of x, you always get to the exact same thing here when you didn't vary, meaning that it is well defined. There's further refinements in the partitioning. If you look at the last video or the video on, if I switch the order of them, but the video on the skip pattern merge and showing that that was sufficient and worked, that is all good. So it really, it is preserved by a very similar argument. So basically what we have is we have a, this is called, so Rx, so polynomials with real coefficients. Actually, it's called a polynomial ring when we put in addition and multiplication in there as structure, as a structure. And we get that that if we do a skip pattern merge by doing multiples of another polynomial, in fact, we could replace this x plus 2 with any other polynomial at all, something like this, so multiples of x plus 2 within the polynomials itself, you actually get another ring where addition and multiplication is preserved. Now, the interesting part about this is actually looking at what the representatives look like, what the chunks look like. It actually looks like remainders after you divide by x plus 2, but that's for another time. Um, but it allows you to truncate things and look at things more up close sometimes. And we'll be seeing uses for that when we do modular arithmetic. This is where we're modding out by a polynomial itself, and it has some good uses there. Thanks for watching.